Hello everyone, welcome back to a new video. Last time I discussed some basic x86-64 assembly programming techniques, and I covered while loops, callee save versus non-callee save registers, some commands and details, and I started off by writing a simple hello world program. So just to quickly review, in every single x86-64 assembly function, we define a function by typing .global function name and then function name : and then at the beginning of every function we should have push q rbp and move q rsp rbp to save the frame pointer, and at the end of every function we need to have leave to essentially undo the previous commands that I mentioned. And also at the end of the function, at the end of the function we need return, which pops the return address and jumps to it. So today I would like to cover some basic arithmetic operations in detail. So this is a cheat sheet that I found online. You can easily locate this by searching up x86-64 cheat sheet on Google, and you should be able to find this. So it gives you a list of registers. On the server that I'm working on, it's 64-bit architecture, so we're using 8-byte registers. And for example, if you want to access the first 4 bytes, you can use EAX, or the first 2 bytes AX and first byte AL. But today I want to focus on arithmetic operations. So inside operations.c, I have defined 5 functions: addition, subtraction, multiplication, division, and modulus. For divide, this function will return the quotient, and for mod, it returns the remainder after division. So I'm going to call these functions in this C program, and then I'm going to print them. So x plus y, x minus y, x times y, the quotient of x divided by y, which is equivalent to the floor of x over y. We're going to just going to be working with small positive integers here. So x is 10 and y is 3. And also, finally, the modulus. So x mod y is the remainder after dividing x by y. Okay, so we see that the functions are defined in the C file. And if we go into the assembly file here, I've already declared these functions here, and I added the 4 lines to all the functions, where the 4 lines that every single function in x86-64 assembly should have. So we see we have all 5 functions here, and since we're working in the text memory section where the code is being stored, I have .text as the first line in this file. Okay, so let's first try to implement addition. So we see here on the cheat sheet that add SD adds source to destination. So it basically moves the adds the content in the source register here into the destination register. So remember that RDI is a special register that stores the first argument passed to the function, and RSI is another special register that stores the second argument passed to a function. So what we want to compute, first of all, the first argument is x and the second argument is y. So we want to compute x plus y and return it. So we should move RDI into REX, because remember that REX is a special register that stores the return value. So whatever value you want to return, just make sure you move it into REX before leaving and returning. So move Q RDI REX moves the first argument into the register REX, and now we want to add the content inside the second argument, which is stored in RSI. We want to add that into REX, which previously stored a value of RDI, so now we add RSI into it. So this would evaluate x plus y. Okay, and this is all we need because REX is the return value and we stored the result we wanted to store in here. So for subtraction, it is quite similar. Move the value in the first argument into REX, and then now we want to use sub Q for subtraction. Subtract RSI from REX, because if we look at the cheat sheet here, it tells us that sub SD subtracts the source from the destination. So we want to subtract y from x, so that's why we first move RDI into REX and then we subtract RSI from REX. So that completes the second function. For multiplication, again, it's very similar. Move RDI into REX, and then I mul Q RSI REX. And the reason that we're prepending all these commands, so you see here it just has sub and add, but we have add Q, sub Q, I mul Q, because we're working with 8-byte registers. All of these registers that start with an R are 8 bytes long, so that's why we use like push Q, move Q. Okay. And then for division, it's a little bit trickier. It's not exactly the same as previously, where we have 2 registers. So for division, since we want to compute x divided by y, x is the first argument, we need to make sure that we move the first argument into REX. We need to make sure we do this. And then for division, we're just going to be using unsigned division since we're working with small positive numbers here. And when we use IDivQ, you notice that it says IDivQS. So previously it's always like S and D. There's a source and there's a destination. But for divq, there's only one register. That's because the register that you want to, that's going to get divided by must be stored in REX. That's fixed. So what this would compute is REX divided by whatever the register S is. And the quotient is stored in REX, and the remainder is stored in RDX. So before we do divq, we want to make sure that we move 0 into RDX. 0 RDX. If we don't move 0 into RDX, then the results may be incorrect. We want to make sure we do that. And then now we do divq RSI, because RSI stores the value of the second argument, and we want to compute the first argument divided by the second argument. We want to return the quotient of that. So we do divq RSI. And since the quotient is already stored in REX, and that's exactly what we want to return for the divide function, then this completes this function. And then for mod, it's very similar. So I'm just going to copy the code over here. So these 3 lines will be the same. We need to do the division to get the remainder, but we need to make sure that we're returning the remainder instead of the quotient for this function. So we need to move the remainder, which is stored in RDX. We want to move it to the register RAX because we're returning the remainder and not the quotient for the mod function. Okay, so we have implemented all 5 of these functions in assembly, and let's try to test it using the previous C program that we wrote. So gcc-static-o, we're going to name our executable operations.out, and then operations.c, operations.s. Okay, so we see that the output is expected, is as expected, because x is equal to 10, long as y is equal to 3, so 10 plus 3 is 13, 10 minus 3 is 3, 10 minus 3 is 7, sorry. 10 multiplied by 3 is 30, and the quotient of 10 divided by 3 is 3, because 10 is equal to 3 times 3 plus 1, and the remainder is obviously 1, so this is correct. Okay, so that's what I wanted to cover for basic arithmetic operations. And something else that I want to go over for this video lesson is some bitwise operations. So let's go to C function, C program here. So these are some examples that I included. So let's say that x is equal to 16, which is equal to 2 to the power 4. So if we write it as a binary number, then it's 1, 0, 0, 0, 0. What shifting to the right means that we're gonna move the 1 over. So basically it's just shifting the bits 1 unit to the right. So we see here previously we have 4 zeros, and after shifting right by 1, we have 3 zeros instead. So the result will be 2 to the power of 3, which is equal to 8. And similarly for shifting left, we move the bits 1 more unit to the left. So instead of having 4 zeros, we have 1 more zero, so we have 5 zeros now. And 2 to the power of 5 is 32. And then for bitwise complement, right, bitwise complement, if we have 128 and which is in binary is 1 0 0 0 0 0 0 0, and the complement is just flipping the bits, so ones become zeros and zeros become ones. So the complement of 128 is this, which is 127. And then these are bitwise exclusive OR, bitwise OR, and bitwise AND, respectively. So the binary representation of 8 and 15 is 1 0 0 0 and 1 1 1 1, respectively. So if we were to evaluate the bitwise exclusive OR, then we compare these two numbers bit by bit. So for the least significant bit, we have a 0 and a 1, and for exclusive OR, that value is to true, so the result is a 1. For the next bit, we again have a 0 and a 1, so it's going to be 1. And then for the most significant bit, we have two 1s, 1 and 1. And exclusive OR is false if both inputs are true. So so these two bits correspond to a 0 in the bitwise exclusive OR. So the result is 7. And for bitwise OR, then as long as one of the two inputs is true, then the output is true. So by repeating the same process, comparing these two numbers bit by bit, we get 1 1 1 1, which is 15. And then for bitwise AND, same thing. We compare bit by bit, and the AND is only true if both inputs are true. So all other bits are 0 except for the first bit, because these two bits are 1. So the output is 8, and we can verify this by compiling it. Okay, so we see that the output is exactly what we expected it to be. And basically what I want to do now is implement this in assembly. So we're gonna have to define a few strings for the same output. Let's call this file bits.s.text, and I'm gonna define my strings here. But before defining the strings, let's define the function pair, make sure we have everything that we should have in any function. So these lines. Okay, and we need to have these strings. So let me just copy these over. Okay, so I'm just gonna name these string 1. Okay. And then string 2. String 3, string 4. So 6 strings in total. So let's see. Okay, so let's copy over the strings. So these are all the strings that we need. And let's see, we begin by letting x be equal to 16 and doing a right shift by 1 first, and then doing a left shift by 1. Okay, so since we're going to be calling printf, let's just push some callie saved registers here. So the registers R12 to R13 R14, sorry, are all callie saved registers, and R15 is also callie saved, but I'm just gonna use RBX. Okay, so since we're saving these registers in the beginning, we have to make sure that we pop them in reverse order at the end of the function. Okay. So let's see. Let's let x be equal to RBX, y be equal to R12, and then let a be R13 and b be R14. Okay. Okay, so we begin by moving 16 into x, because we let x be equal to 16, right? So in the cheat sheet here, we want to do a shift to the right. Yeah, shift to the right by 1 unit, so we can use SHR. So let's do that. SHR. Well, actually, we're gonna reuse the value of x. So let's move RBX into a temporary register. Yeah, and then we can perform the right shift on this register instead. Okay. So to print the value, to print the value, we need to call printf. So let's actually store this in RSI instead, since this would be the second argument. And we want to move str1 into RDI. And since we're calling printf, make sure to 0 rex. So this is basically printf and then okay. Alright, so let's test to see if this is working. Bits asm.out. Right. Okay. So yeah, so we see that the result agrees here. Okay. And next, let's repeat the same process, but doing a left shift instead. So let's, we're gonna move RBX into RSI again, but this time we're gonna do a left shift, unsigned left shift. Okay. Okay, so this is left shift, so shift left, right? Shift and then L stands for left, and shift R stands for right. Okay. Not bits.out, bits.asm.out. Okay, so the result is correct. Alright, so let's move on to the not. So the complement, basically, bitwise complement. I'm just gonna copy these lines over since we're gonna be printing the result. It's gonna be with string 3. Okay. And okay, so the next register, Y is, I believe, 128. So let's move 128 into R12. Okay, so yeah. So you can actually simplify all of this. I think we actually don't need this many registers, but it doesn't hurt to use these. Alright, so because we want to print the complement, I'm just going to move 128 into R12 and immediately move R12 into RSI, which is for passing the second argument. And we're just going to use the command not. Okay. So let's see. Oh well, see, this is an issue because in our C program, if you remember, in our C program, I specifically chose Y. It's a character, so that means this is only 1 byte, right? So it's only 1 byte, then it's only 8 bits long, and when we do a negation, it's gonna be this, right? But in the assembly, Y is being stored inside a 8-byte register. So it's 8-byte register, that means it's 8 times 8 equals 64 bits long. So all the preceding zeros, in this case we would have like a lot of leading zeros. When we do the bitwise complement, all these zeros will become ones. And we see that it's negative because the first bit, right, the most significant bit is going to be a 1, and that's indicating that it's a negative number. So that's why we see a big negative number here. Okay, and I believe I can fix this by using, let's see, so instead of using R12, we're gonna use the equivalent, the first byte only. So let's try this instead. R12B, and okay, yeah, so let's not move this yet. So we're gonna use a 1 byte register, and then we're gonna try not R12B. Okay, so this should then correctly get the bitwise complement. All right. Okay, and then we have to move this into RSA, but remember R12B is a 1 byte register, and R12B is 1 byte, but RSI is 8 bytes, right? So something that we can do is move 0, I believe it's Q here, yeah. So move 0 extend from byte to quad. Let's see if I remember the syntax exactly. Yeah, let's give this a shot anyway. Okay, let's see. Yeah, I think it's incorrect. Okay, so the mistake is actually here. Because we're using 1 byte, then it should be move B. Okay, so now we see the correct result is being displayed. Right, like if we compare it to other output, okay, so we see all of this is correct. And then let's finish this up. So then bit.s, let's try to finish the exclusive bit, the bitwise exclusive OR, bitwise OR, and bitwise AND all at once. So A is 8 and B is 15, right? Let's double check. Yeah, okay. So let's do the bitwise exclusive OR first. Again, we're just going to be calling printf again, so let's copy this over 3 times because we're going to make 3 more calls to printf. And string 4, string 5, and string 6. Okay, so in this part, we're going to implement the bitwise exclusive OR. Okay, so yeah, XOR. So let's do this. Because it's gonna get stored in the destination here, so let's store R14 into RSI since we want to print it out, and this is gonna be the second argument to printf, right? So we're gonna do XOR R13 and RSI. Okay. And then basically same thing here, and then we're gonna use OR XOR, yeah, it should be XOR Q since we're working with 8 bytes. And then R13, RSI, right, move Q, R14 to RSI, and then and Q, R13, RSI. Okay, so let's try this. Alright, and we see that the output is now identically the same now. Alright. So I hope that you understood everything we discussed in today's video lesson. I'm starting to make a series of x86-64 assembly programming tutorials. So this is the second video in this series. If you haven't watched the first video yet, make sure to check that out. In that video, I pretty much assumed that you have zero experience with x86-64 assembly programming, so I explained some commands in detail. If you enjoyed this video, don't forget to like and subscribe, and I'll see you in the next one.